Let's take a look now at the method of short circuit time constants example. We'll take a look at an example. And to save a little time, it's a little sloppy, but again, I excuse my penmanship. I have a hard time writing on the glass with the pen here. The pen tends to slide around a little bit. And as you know, I'm not the neatest person in the world, but I hope you can make sense of this. So we've got a common emitter amplifier. Okay, we've got a VSig, which the book calls V-signal. So we've got an input. R-sig is the source resistance of that signal. We've got CC1, which is a coupling capacitor. This is voltage divider biased common emitter. So we've got RB1 and RB2. We've got VCC up at the top there. That's our DC biasing voltage. We've got RC, the collector resistor. We've got RE, the emitter resistor. In parallel with the emitter resistor, we've got CE, which is bypass capacitor. We've got CC2, which is another coupling capacitor, and we've got the load where we're taking our output. So we can take that, and we can. I've drawn a T model below. So you can see here we've got the different components. Again, for the T model, what you do is you basically ground the DC supplies. So you RB1 drops to ground. RB2 was already at ground, so now you've got RB1 in parallel with RB2. We're calling that RB, that's in red here. We can identify a current. 1 minus alpha times IE is the current at the base. We've got IE, which is the current through little re, and little re is in series with the parallel combination of RE, the emitter resistor, and CE, the emitter bypass capacitor. We've got CC2. Oh, I just noticed I forgot RC. I'm going to draw RC right here. So RC, our collector resistor, was originally attached to the DC supply, so now that drops to ground. We've got CC2, the coupling capacitor, and we've got the load again where the output is taken. So here's our T model, and what we want to do, we went through the steps in class on how to apply this method of short circuit time constants. So let's do that. This is the circuit we're going to be working off of. So let's make a new page, and let's say we're going to applying the method. Applying method of short circuit time constants. And just as a reminder, we said with the short circuit time constant stuff, what we're doing is we said that in many circuits, the caps interact, making it difficult to determine what the pole frequencies are. And for this reason, what designers will do is they'll sometimes estimate the low frequency cutoff without the need to determine the exact pole frequencies, what we just went through in the past here in the earlier lecture before this. So what we're doing is we're coming up with a little, it's a short circuit method, and it's a little bit of a shortcut, I guess. So let's look at the steps. Again, you need to just follow the procedure. First step, set the source to 0. Okay? Second step, you consider each of those caps one at a time. You can say consider caps one at a time, and find the time constants. Okay. For CC1, let's look at that first. CC1, that's that first coupling capacitor. We want to draw the circuit. As you've come to realize now, I'm a big fan of drawing the circuit, redrawing circuits. So for CC1, what are we doing here? What we're going to do is we're going to short all caps. Let's say all caps shorted. except CC1. Okay, we end up with something like this. We end up with, okay, we're shorting the supply, but we're not shorting the source resistance of the supply. So R sig stays in there. Okay, CC1, that stays. We got RB. And we're not dealing with a MOSFET here. We're dealing with a BJT. And if you recall back in chapter 3, okay, we said a MOSFET at the input resistance at the gate was infinite. It's not the case with a BJT. There is a finite resistance at the base. And that's what that is. Okay, so we can make a little note here. And again, this comes out of chapter 3. So this is something you covered last semester. But we can say R pi here is the input resistance at the base when CE, the collector and emitter, the collector to emitter, let's say, is short-circuited. Okay, so I mean, you just got series parallel stuff going on right here. So we can say CC1. Let's write it out here. CC1 sees resistance. We'll call it RC1. We've got RB. That's that parallel combination of RB1 and RB2 in our original circuit, in parallel with R pi. Okay. Oh, one other thing I forgot to mention. R pi, let's draw a little arrow here, will be given. Okay, it's a spec. So we got RB in parallel with little R pi plus R sig. Okay, so we're calling that RC1. And the time constant we'll call it tau C1 is RC1 times CC1. Okay. We can do the same thing now for CE. So let's make a new page here. So we can say for CE, the emitter bypass capacitor on this bipolar junction voltage divider biased bipolar junction common emitter circuit. Okay, so we can say for C little e, again all caps, shorted, except C. We end up with this for our circuit. We end up with an equivalent resistance here. I'll write what that is in a minute. We end up with little RE here. Okay. We'll talk a little bit about what that is. RE, big RE, which is just that emitter resistance, and CE, that emitter capacitor. Okay. Now, right here, this equivalent resistance right here is going to be RB in parallel with R sig divided by beta plus 1. Okay. What else do we have here? Little RE. Let's say recall Again, this is chapter 3 stuff, both of these actually. Chapter 3, little re is approximately equal to 1 over the transconductance, which is given. Okay, so we can do the same thing now. We'll do the same thing we did for CC1. We can say RCE, okay, this is the resistance that CCE sees. So RCE is going to be RE, looking at our circuit here. Again, series parallel stuff. Parallel with little re plus RB in parallel with R sig divided by beta plus 1. Okay. Once you got that calculated, we can say tau CE is equal to CE times RCE. Okay, so let's look at CC2 now. New page, so we can say for CC2, again all caps, shorted, except CC2. So we've got RC, we've got CC2, RL, okay. Same thing, we can call it RC2, we can say RC2 is going to be just equal to RC, they're just in series, plus RL, and tau C2 is going to be equal to CC2. I keep writing more than one C here. We'll use the book notation, CC2 times RC2. Okay, RC time constants, again, is all we're calculating. Once you know all 3 time constants, okay, you can calculate, maybe estimate is a better term here, but we'll calculate the 3 dB frequency. FL, okay? It's in hertz, okay? So again, it's just going to be, we're going to do a conversion. Omega L over 2 pi is equal to 1 over 2 pi times 1 over the time constant for CC1, so that's CC1 times R1 plus 1 over the time constant for CE plus 1 over the time constant for CC2. So it's CC2 times RC2. Okay. So that's it. That gives you a pretty nice little estimate. Now, there's a couple of things we want to notice here. I'm going to write it down here. Okay, we can say, notice the lower value. Now we say the value of the time constant. The reciprocal relationship, 1 over the time constants in each case. Notice the lower the value of the time constant associated with a particular cap, the greater the contribution to FL. Okay, and we've got a very similar thing going on here. We're looking at a BJT here, but so we can say in a common amp, common emitter amplifier, this is usually the bypass capacitor. Just like it was usually the bypass capacitor in a MOSFET. Usually CE, that's the bypass capacitor, because the associated resistance RCE, that's the resistance we calculated, is typically small. All right, there you go. So we will stop here, but that's how you do this. And again, what you're doing is if you really think about this, we're not calculating individual cutoff frequencies for each individual capacitor. We're combining them, and that kind of makes a lot more sense if you think of it. This is a combined effect or a combined impact on the circuit. So I'm going to stop this